Any questions? Okay, so one problem we have when we are dealing with fermions is that fermions should be anti-commuting, not commuting. So, but if we use all this formalism over here, we just recover ordinary functions, they commute with everything else. So we need something that doesn't commute, that anti-commutes. So that is where we invent so-called Grassmann algebra. So what is this? I just claim that I have these symbols. Let me even write n of them. What are they? Well, they're just symbols, nothing else. But these symbols have this nice property that, for example, if you just take two of them and change their places, they change sign. They anti-commute. They're anti-commuting symbols, so-called Grassmann variables. And if you take the square of any one of them, well, the anti-commuting property tells me that it should be also equal to minus itself, which tells me that it should be 0. Now, what is the algebra? Well, okay, before going to the algebra, I will claim that I can multiply them. A being a complex number, any complex number. And I can also add them. And all such combinations form what I call my algebra. Any non-zero product, any linear combination of non-zero products is my algebra. And weird it might seem, this is consistent. Mathematicians, they nicely prove that what we define here is nice and consistent. I can talk about, let's say, for example, what does this members of the algebra look like? Let's say for n is equal to 1, my algebra is any combination of this form. This forms my algebra. Well, you can talk about, let's say, functions. Schwarz doesn't like to note the terminology functions. In most places, you will see functions of Grassmann algebra, Grassmann variables. You see, any function, if it's a well enough behaved function, you can write it as a Taylor expansion. Its derivative at 0 times theta, its second derivative at 0 at theta squared, etc. Theta cubed, theta fourth, but theta squared is 0. So this term is 0. This is, all the higher order terms are 0. So any function of a single Grassmann variable is just some constant plus another constant times theta. And this is not an approximation. You see, before, in the last hour, we expanded our path integral in epsilon and kept only the first term. That's an approximation which is valid for epsilon small enough. This is exact. I don't have any other terms in my expansion. If I have a Grassmann variable, a function or a member of an algebra that depends on two Grassmann variables, I will have some a plus b theta 1 plus c theta 2 plus d theta 1 theta 2, and I don't have anything else. This is the most general possible form of a member of my algebra of two Grassmann variables. Now, when you look at the path integrals, well, we need to define how we integrate these functions, these variables. Let's say, suppose I have a function of an integral over the Grassmann variable theta of f of theta. Well, this will be d theta, a plus b theta, because that is the most general f of theta, which is a d theta plus b d theta theta. So it's enough to define these two integrals. So if I know these two integrals, then I know the integral of any element of this algebra of single Grassmann variable. And what else do I want? Well, I want this property that d theta f of theta is equal to d theta f of theta plus c. C being some number. What does that tell me? Well, the left-hand side is a d theta plus b, the integral of d theta theta. Well, the right-hand side is a plus bc so this property, which I underlined twice, is a property of integration. I want the integration of Grassmann variables to also have the same property, just like the integration of ordinary functions. But this tells me that the integral of d theta should be 0. It doesn't really tell me what the integral of d theta theta is, but it's just, you can think of it as the normalization of this integral. You can define it to be 1. And similarly, if you want to talk about the derivatives, the derivative of constant should be 0. And the derivative of a variable with itself, with respect to itself, should be 1. So this integral has this weird property that integration and differentiation are the same thing. And if you have more than one Grassmann variable, you can define these integrals. This should be 1. This is defined as 1. If you just start from inside, this integral is 1. Again, this is 1. So you can just repeat all the way up to showing that all the integral is itself 1. And you need to keep track of the signs. For example, this integral is minus 1, because in order to be able to take this integral, first you have to anti-commute theta 1 and theta 2. This integral becomes minus this 1 because I anti-commuted t1 and t2. This is 1. This is again 1. Hence the integral is itself 1. Well, we have Gaussian integrals. Well, I cannot just take the e to the power minus, let's say a 1, 1 theta theta. Yes, we had e to the power minus alpha y squared integral. This is theta times theta is just 0. This is 1. The integral over theta would be just 0. But I can talk about this integral, double integral of e to the power minus theta 1, a1, 2, theta 2. a1, 2 being some number. Doesn't even have to be positive or negative or anything. Which will be equal to d theta 1, d theta 2, 1 minus theta 1, a1, 2, theta 2, which is, the first integral is 0, the integral of 1 is 0. If I want to take the integral of the second term, first I need to change the places of theta 1 and theta 2. That will bring me a minus sign, so this is just a1, 2. So, Also, just to note, for example, theta 1, theta 2, theta 3 is theta 2, theta 3, theta 1. Both are members of my Grassmann algebra. And when this theta 1 and theta 2, theta 3, they just commute like ordinary numbers, ordinary functions. So if I have even product of Grassmann variables, they just behave like commuting variables with everything else. Now, we also define complex Grassmann numbers. Let's say I have theta 1, theta n for some n. And let me assume I have n more Grassmann variables, which I will show as theta 1 bar, theta n bar. So these are, in fact, just completely independent Grassmann variables. I will call, let's say, theta I bar as the conjugate of theta I, just a name. So that the naming I use for complex fields will also have some analog in the case of Grassmann fields. Again, I'm just saying that these are just naming, but the mathematics we define, the algebra that we define turns out to be consistent. We have well-defined integrals, and we will have well-defined path integrals for these variables. Let us also look for, let's say, d theta I bar e to the power minus theta I bar aij theta j. What is this integral? Well, let's see. This is equal to d theta I bar. Overall Grassmann variables I have 1 minus theta I bar aij theta j plus, let me write it in this form first. All these terms. The integral of this is 0. Well, if I have, let's say, 2 Grassmann variables and 2 conjugate variables, in total 4 Grassmann variables, the integral of this one will also be 0, because only for 2 of them I have theta I bar and theta j. 2 of the other Grassmann variables, my integrand doesn't depend on them. So the only possible contribution will be from this one. Let me write it explicitly for that case. N is equal to 2k. What do I have? I have d theta 1, d theta 2, and then integral over the conjugate Grassmann variables, and e to the power minus, well, theta 1, a1, 2, a1, 1, theta 1, plus theta 1 bar, a1, 2, theta 2, plus theta 2 bar, a2, 1, theta 1, plus theta, this is 2, theta 2 bar, a2, 2, theta 2. This is the integral I'm looking at. Well, this will be equal to d theta 1, d theta 2, one minus all of these. I won't write them explicitly. Plus 1 over 2 all of that. Now let me write one more term. And basically that's it. I don't have any other terms. You see, if I try to take the cube of it, I have the product of, I will get terms with products of 6 Grassmann variables, but I only have 4 different Grassmann variables. So any product of more than 4 Grassmann variables will always be 0. I don't have so many different Grassmann variables in my hand. Now this is 0. Our theta 2 bar integral itself will be 0. Well, if you look at this term, it doesn't contain theta 2. So the integral over theta 2 will be 0. Well, for each one of those terms have at most 2 Grassmann variables that appear. The remaining 2 Grassmann variables do not appear in all those terms. So the integral over the remaining Grassmann variables will be 0. Now what is left is possible contributions from this term. Now when you try to take the square, if I take the square of this one, I get theta 1 squared, which is 0. Now, in fact, if you have sum of 4 terms squared, the terms you have will be the square of each term plus twice the cross terms. So what does it tell me? If I take the square of any one of these terms, it will be 0, because I will get squares of Grassmann variables. So these the corresponding terms will not contribute. Well, the cross terms will be, well, there will be 2's in the cross terms, which will cancel this 1 over 2. So I'm not writing the 2's. What are the possible cross terms I have? I have theta 1 bar A1 1 theta 1, theta 2 bar A2 2 theta 2. You see, with this one, the only possible other term that I can multiply and get non-zero number is this one. Because, for example, if I multiply this one with the second one, I get theta 1 bar squared, which is 0. Similarly, if I look at this term, the only other term I can multiply with this one for these cross terms is the one with theta 2 bar A2 1 theta 1. And in fact, that's it. I don't have any other term, any other cross term. Well, what are these integrals? Well, let me look at the first one. Well, you see, these properties here, this integration property, where did I write it? Here. Or let's say, let me first integrate over theta 2 bar. Well, theta 2 bar is over here. I have to anti-commute it over theta 1 and theta 1 bar. That is 2 anti-commutation relationships, so there's no sign change. The integral over theta 2 bar of this term will just give me 1. Then I integrate over theta 1 bar. Well, theta 1 bar is already with theta 1 bar. So again, theta 1 bar integral will also give me 1. Then I have integral over theta 2. Well, the theta 2 should go over theta 1. Remember, theta 2 and theta 1 bar, I had already integrated over them. Well, it goes over theta 1. That brings a minus sign. And then the remaining theta 1 integral, everything else is already integrated over. That just brings me a 1. So this the first term, the integral is, if I counted the signs correctly, it should be A1 1, A2 2. Let's look at the second term. Well, let's see, theta 2 bar integral. Theta 2 bar is over here. I have to commute or anti-commute over 2 Grassmann variables, so there's no sign change. Theta 2 bar integral will just give me 1. Theta 1 bar integral, well, theta 1 bar is already over there, so that will give me just a factor 1. Theta 2 integral, well, theta 2 is already there. It will again give me just 1. The remaining theta 1 integral will also give me 1. So plus A12, A21. So let me take the minus out. Does this look like anything? It's just a determinant. Guys, if you compare this with I do advise you to calculate this integral. This will be pi over determinant of A. One is 1 over the determinant of A, the other one is just the determinant of A. Squared. Well, I don't really care about that power. What is more important is that one is the determinant is in the numerator in the Grassmann case, in the ordinary function case, it's in the denominator. That's something we will use later on. Is there a square or not?
They should cancel for the measure to be valid, right? So maybe there's none, but when we write it like that, I imagine it like I see it like a square. But these should to cancel to have I don't know cancellation.
Well, I look at units. Okay. You see, let's just take z to be some distance, complex distance. So the left-hand side is 1 over the distance squared, distance to the 4. A has units 1 over the left-hand side is distance to the 4. Each matrix element has distance -2. Determinant has the product of 2 elements, so this is distance to the -4. So already 1 over the determinant has the correct units without the square. Right? How do we calculate it? Okay, we didn't look at the Gaussian complex integration. We had Gaussian integrals over real numbers. How do we calculate this one? Problem solving for the problem solving hour. Anyway, so now we have everything, basically. You see, what were our fields at the point y at the time t were basically x at the point y, the variable at the point y at the time t. Now I have eta. This will be my Grassmann variable, eta of y of t. It will be my field. So for QED, let me leave QED for the time being. For the Dirac field, Z will be just the integral over eta, the integral over eta bar. Eta and eta bar are Grassmann fields, or Grassmann valued fields of e to power I s Dirac, the action of the Dirac field. This is now how I define my path integral for the fermions. You see, when we had field, for the scalar field, again, what we had done, we had something that is oscillating at every point. It had a scalar value at every point in space-time. And then we said that, let me just call this my scalar field so that it has a scalar value at every point in my space-time. For fermions, I had to introduce this Dirac field, which anti-commutes. So its eigenvalues, let's say, should also anti-commute. So the eigenvalues of this Dirac field should be Grassmann valued. So at every point in space, I have a Grassmann number valued field, just like the scalar field that I introduced. Now I introduced some other field at every point in space-time, but this time, since they have to anti-commute, the value of that field should be Grassmann valued. And I have to I had this scalar fields. I were integrating over all possible scalar field configurations. Now I'm integrating over all possible configurations of my Grassmann field. Well, how do I integrate over my Grassmann fields? Well, I had already defined my integration, how I carry out the integration. I know how to integrate over them. And hence, this is my path integral. And the result of this integral is some ordinary number. It's a matrix element.
So basically, Grassmann valued fields, that's how we define fermionic fields, right?
Yes.
So I have a huge misconception in this. So Grassmann, we can define a space, let's say a force space that has the ordinary numbers. And we can value fields from those ordinary numbers that we can find scalar fields. Those scalar fields are classical, let's say, and then we quantize them. But in here, we also know that spin is an intrinsic property that we find via quantum mechanics, right? That manifests via quantum mechanics and special relativity. But in here, we are not using any of it. We define a mathematical construction, and we value by extending our space to be valued by Grassmann numbers. We are saying that there are also some fields that can be valued under them, and they can act like a fermion. But Grassmann variable fields are not the physical fermions. They are just somehow under quantization, they act like fermions. So when I try to write let's say classical field theory, let's say the Dirac theory itself, but not quantizing it, just writing the field of fermions, then we are saying that there is a classical theory of fermions. But we know that spin is an interesting property that we don't see it from the classical notions. Right? So I cannot understand that how this quantization procedure purely from mathematics give the same notion.
Okay, so
I'm not sure it's a good question, but
let me first start by saying that the Dirac equation doesn't have a classical limit.
Yeah.
So there's no classical Dirac equation. Basically, because they are anti-commuting in classical physics in our everyday life. We don't have anything that anti-commutes. Everything commutes. So when we take the classical limit, what makes sense are not the Dirac field itself, but the bilinears, the products of two quark fields. For example, we define the charge of a Dirac field. It's a bilinear in fields. Everything that we can actually measure will be a bilinear in the fields. And hence they have somewhat a classical corresponding quantity, which commutes with everything. Secondly, what is quantization? So when I say quantizing a system, what do you understand from that?
Canonical quantization, imposing canonical relations.
Great, that is one way of quantizing the system. Saying that, okay, I have a Lagrangian, this is my field, there is a corresponding conjugate momentum, and when I impose the commutation relations between the field and the conjugate momentum, I have quantized my system. That is just one way of quantizing the system. Now, here we are actually doing the second way of quantizing the system, just claiming that the matrix elements are given by the path integrals. That already quantized my system. And in fact, in the scalar case, we had already seen that the what we had, the terms that come from the non-zero commutation relationships in the Schrödinger-Dyson equations, they are already inside the scalar, inside the path integral formalism. So in that sense, they are also equivalent to each other. So now I have quantized my system. Let me put it this way. I have written down a system which is a quantized system of Grassmann variables. Now, do they correspond to spin 1/2? I didn't yet claim that. But the only thing I claim is that, okay, I can write, when I'm writing path integrals, I don't have to stick with classical functions, just ordinary, not classical, just ordinary functions of commuting functions. I can also come up with this algebra, and within this algebra, I can write down a path integral for within this algebra. Again, this path integral is a number, just an ordinary number. You see, if you just go back over here, the path integral, at least in the non-interacting case, will be nothing but Gaussian integrals of this form. And the result of those Gaussian integrals, or any, even if I have other terms in that expansion, all those terms will amount to being some number. Just commuting number, ordinary number. So this path integral, which I claim gives me my matrix element, and that claim is what we call quantization, actually gives me just a number, and my matrix elements should be just numbers. Okay, does this object correspond to spin 1/2 particle? How do you tell that?
By their transformation.
Their transformation or their interaction. How will they transform? How will they interact? That is something we have to look for.
So this correspondence from dynamical Grassmann fields and the fermions is something that we make by construction. We are saying that
Okay, and another comment, for example, you said that, okay, scalar fields are my scalar particles. They're not. Scalar fields are just things that we use to represent actual particles. Well, the same thing here. These Grassmann numbers are not my particles. They are mathematical objects I use to represent physical objects. Now, can I identify a Grassmann field with the electron? That's a different story. That's a different question, which we might be able to go in somewhat detail later on. So if I claim that I can use a Grassmann field to represent my electron, I should also make sure that it has the same properties. And which properties are we talking about? Well, it's interactions, let's say. Does it interact just like an ordinary electron? Does it have spin 1/2?
we could directly check it right now. We just need some dA and then Maxwell interaction with the Dirac. If it's really Dirac, then if it's the same, it's okay. This is how we see it, right? Somewhat.
Now let me write the QED Lagrange, QED path integral. Well, there are a couple of more things I need to do. Now what happened, eta just became a Grassmann valued spinner. These etas over here are 4-component spinners. Each of the elements of these 4-component spinners should be a Grassmann variable. Now these Grassmann variables will correspond to my operators. But remember, when we were expanding the Dirac field, we had the operators multiplied by spinners. So now this eta is basically corresponds to my operators are replaced by their eigenvalues, which are Grassmannian variables. The spinners are here. But spinners already tell me that they are spin 1/2.
now we can say we can say to check the dimensions, right, and see its spin 1 over 2 from here. Now,
Dimensions.
like mass dimensions.
We can look at the interactions.
Okay.
It will just interact just like a spin 1/2 particle. It will transform like a spin 1/2 particle because the spin 1/2 property is not in the operators itself, it's in the spinners. Spinners are here, the spinners appearing here are just the spinners that we studied last semester. Well, you were not here. But the 4 component spinners, they transform just identical to those spinners. If you want your term to be invariant under Lorentz transformation. So here this eta and eta bar, they contain spinners for spin 1/2 particles multiplied by creation, annihilation and creation operators whose eigenvalues are Grassmannian numbers. Yes, remember when we were looking at writing the matrix elements in terms of path integrals, we had to find states who were eigenvalues or eigenstates of my fields with eigenvalues given by just functions, ordinary functions. Here I'm doing the same thing more or less here, but I'm looking for states or states of my spinners, fermionic fields. But since my fields are anti-commuting, the eigenvalues themselves should anti-commute, and hence I need to invent these variables, anti-commuting variables. But the spinner part is multiplying these operators. And how do we say that they are spin 1/2? By just looking at their spinners. Well, spinners are already here.
So these etas are a spin 1/2 representation of the Lorentz algebra in a different space than.
Well, let's see. A spin 1/2 representation of the Lorentz algebra are the spinners. Etas are just numbers 1, 2, 5, just like them, but they anti-commute.
But do they not transform as spin 1/2?
What do you mean by transform like spin 1/2?
I mean, aren't these fields defined over all space-time?
Yes.
So,
Well, these etas are There are 4 components spinners. They still have 4 components. Each one of those components is a member of my Grassmann algebra. And now, whatever I did in the case of scalar fields, I can do scalar path integrals, I can do with my Grassmannian path integrals. For example, let's look at the Dirac field only. Let me define the generating function. There's an integral over all these Grassmann fields of e to power I d4x eta bar I del slash minus m eta. These are at the point x plus, let me say j eta, jx, j bar x eta, x plus eta bar of x, j of x. Basically, I have 2 different Grassmann fields, eta and eta bar. For each one of those fields, I have a different source term, j or j bar. And let's say if I would like to calculate this matrix elements, this will be just 1 over z 0 That's the normalization. The derivative minus the derivative with respect to j of x. Let's see, if I want to get psi bar, which is eta bar, so I need to take the derivative with respect to j of x, x1, and derivative with respect to j bar of x2. Well, if you would like to be more explicit, you can say that, okay, let me look at this, the alpha and beta index, this is the alpha and this is the beta index.
We should pay attention to order of derivatives.
Yes, we should pay attention to the order of the derivative, so let me check the order. Let's see, if I first take the derivative with respect to j beta, or j bar beta, it will bring down an eta, or psi of x2, so let me check the order. If I first take the derivative with respect to j bar, it will just bring me, j bar will bring me a factor of eta of x2. Now, if I want to take the second derivative, first I need to take anti-commute the derivative with this eta. So that will bring me a minus eta x2. Now the derivative with respect to j of the exponent, note that if I want to take the derivative with respect to j, I first should anti-commute with eta bar. So that will bring me a minus eta bar x1. So this will be psi of x2, psi bar of x1. So I should change the order of this differentiation. Well, this is
So will they drop in front of the explanation?
it doesn't matter.
Doesn't matter.
You see, all the factors in the exponent is bilinear. So all Grassmann variables commute with whatever appears in the exponent. There are two of them, an even number of them.
Yes, but if you wrote eta x2 after the explanation, the action, then the order.
Oh, okay. So what you are saying is, let's say that, okay, rather than putting it over here, so your friend is saying that I can put it after the exponent.
Can I?
Hmm?
Can I?
Why shouldn't you?
Yeah. So
It commutes. So if you put it after the exponent, now this derivative with respect to j of x2 will bring you, if you just look at the derivative, j of x2 brings minus eta x2. No, x1. No, sorry, this is x1. So basically, I get the same thing. No?
We have the minus, when we switch, we have the same thing.
So yes, but okay, I miss why we have a plus sign for x2 but minus 1 minus 1. So what changes?
Here, you see, when you want to take the derivative with respect to j of x1,
Yes.
you see j is after eta bar. So
Okay.
I have this derivative.
So why would okay.
So this is
Mhm. Okay. Yes. So why didn't we have a plus sign in the first version? We have minus theta x2. Oh, okay, so we have to switch with theta x2 as well, right? So
yeah. You see, you mean this one?
okay.
You see, that one is derivative with respect to j bar.
Yes.
J bar is first.
Okay.
I don't have to commute j bar and eta.
Yes.
So it's a plus.
Okay, thank you. Sorry.
But then, if I want to take the derivative with respect to j of at x2, first I have to commute with this eta, so it became -1. And then I need to take the derivative of the exponent. J is over here, I have to commute with eta bar again, that brings another minus sign. So that's why I have the minus eta bar x1 over here. Or, as you pointed out, I can put this eta 2 after the exponent, so that if I want to take the derivative with respect to j of x2, I don't have to commute with eta x2. But then, now this x1. But then when I take the derivative of the exponent, I have minus eta x1. So here I have minus eta x1, one of them is eta bar, this is eta bar. Minus eta bar, eta 1, minus eta 1 bar, eta 2. Here I have plus eta 2, eta 1 bar. Well, they anti-commute, so they are equal. So it doesn't make any difference whether you put this factor before the exponent or after the exponent, it shouldn't make any difference. Okay, so I will leave it to the next lecture. We will basically do the same thing. So my question will be, let me shift eta and eta bar by some unknown function. What should be that unknown function so that I get rid of the linear terms in my fields? And basically I will recover exactly the same result. I can use this generating function to derive all the Green's function. I will get the Wick theorem for these Grassmann field, the spinor fields, etc. And then, you see, here, there's something I didn't write, strictly speaking. It's not strictly correct. You see, we are summing over all paths, all physical paths, let me add. They don't have to satisfy our equations of motion, etc. So what is physical are the electric and magnetic fields. When I'm summing over all vector potentials, I am summing over all possible electric and magnetic fields, but I'm overcounting it. Because there are infinitely many vector for a mu fields that corresponds to the same electric and magnetic fields. But instead, I should actually sum over only one of those fields. Now, we will see that it doesn't make any difference. But that is for our next hour, let's say. And we will see how that term, remember we had added this 1 over 2 psi del mu a mu squared term, how that term comes about. And there will be also a few hints about what will happen if we don't have U1 field, but a more general non-abelian gauge theory. That is something we will do towards the end of the semester also. Yes?
When we take bar on J or another Grassmann number, it defines an inner product, right? Because it maps it's a real number. If I'm not wrong. So G bar n is a real number.
It's not a real number. It's a member of the Grassmann algebra. But it commutes with everything. Since it's a bilinear, it's not a real number. So it's not an inner product.
Then path integral is a Grassmann number.
Path integral is not a Grassmann number. You see, we define the integrals of the algebra. This path integral is just a integral over many different Grassmann variables. So you see, the integrals are just real numbers. The exponent here is not a real number. It's a member of the Grassmann algebra. But the integral is some complex number. So see you next week.